Section 4.2, the mean value theorem. The Rolle's theorem says, suppose that function f of x is continuous over the closed interval a through b, and differentiable at every point of its interior a through b. If f of a is equals to f of b, then there is at least one number c in a through b in the open interval a through b, at which f prime of c is equals to 0. So we can see here to the left side an illustration for this theorem. There's this curve right here, which we can consider this to be the function f of x. And it says that if we consider the interval from a through b, the closed interval from a through b, including the a, including the b, that's what it means. And if the function is continuous over this closed interval and differentiable at every single point of every interior point of this open interval, so not including the, it may not be differentiable at a, it may not be differentiable at b, but at every point in between these two, then it says that there has to exist at least one point c on this curve that is within this interval, where the derivative of this function evaluated at this value c is going to be 0, meaning that there's going to be a tangent line passing through that value c where the slope is 0, right? That's what it says. Also says that there are some exceptions to when they may not be tangent line. So, for example, letter A here says is continuous at an endpoint of A and B. What if it's not because you see the definition says that the function has to be continuous over the closed interval, including A and including B. But if it is not continuous, it's discontinuous. Actually, here at A, you can see here the open circle, and this point being removed. Then, if the function is not continuous over the closed interval, including A and B, then Rolle's theorem cannot even be held to be true. Second example, discontinuous at an interior point. What if within the interval there is a point where you see this discontinuity? Then the theorem does not hold anymore. There will not be a horizontal, not necessarily going to be a horizontal line or a horizontal tangent line passing through one point on this curve where the slope is going to be 0, or the derivative evaluated as that number is going to be 0. And then C says, what if it is continuous on A through B, but not differentiable at an interior point? So basically, the different types of discontinuities that we already talked about at some point or another before: removable discontinuities, cusps, corners, holes, jumps, breaks on the graph. If within the interval, at any point in between or at the endpoint, you see that this makes the function not to be continuous because you see any of these three scenarios, then it's not a guarantee that there has to be a horizontal line or a horizontal tangent line, as the hypothesis of Rolle's theorem states. Okay. Now moving on to another theorem that is also important. Based on what we read right now, we have here the mean value theorem. Very similar to the one that we read. Suppose that there's a function f of x that is continuous over a closed interval a through b and differentiable on the interior intervals, on the interval's interior points a through b, but not necessarily has to be differentiable at a and b, just in between. But it has to be continuous all the way from a up to b, including the endpoints. Then there is, it says, at least one point c in the open interval a through b at which f of b minus f of a over b minus a is going to be equal to the derivative of the function evaluated at c, at this point c, right? So what you have before the equal sign is basically talking to us about something like what you see here on the illustration. So you see that there is this secant line passing through A and B, and that's where this part comes in. This represents that secant line, or the slope of this secant line at these two given points or given values. And then the right side means that there has to be some value c in between these two, or some value x as you see it here in this picture, where if you continue like just trying to see how this x is connected on the actual function, then the derivative of this function at this number x or c as they're calling it here, it's going to be a tangent line. So it says that the slope of the tangent line is supposed to be at this given value in between this interval. So we don't know what this number is, but we know that it exists if the function is continuous on the closed interval from a through b, if it is differentiable on the intervals interior from a to b, then we know that there's at least one value x or one value c, where if you calculate the slope of this tangent line passing through this single value on the function, it has to be the same thing, has to be the same slope as this secant line passing through a and b, which are the endpoints of this interval. Okay, so that's what they're saying, that these two are going to be the same slope. Okay, and that's basically what this is saying here. So this first problem says, does the function satisfy the hypothesis of the mean value theorem on the given interval? Give reasons for your answer. So does the function satisfy the hypothesis on the mean value theorem? So if I reread the mean value theorem, first of all, the function has to be continuous over a closed interval. We are given a closed interval here to analyze this function. We're not going to look at the entire function. If I would graph here on the y equals this function, I don't know why it doesn't want to graph it. Don't know why it doesn't want to respond. Okay. Let me close my calculator and start again. It's okay there. I don't know, it got stuck. So if you put x raised to the 4 over 5, if I look at the whole function itself, remember the types of discontinuities that we reviewed right now? This right here at the center, at the origin, that could be something like letter C, that kind of discontinuity where there's sort of a cost. So then we may say that this function is not continuous, but now if you cut it to only this interval, so if I go to the window and the x-axis, I'm just going to cut it from 0 to 1. It's going to look a little strange, right? But I mean, I'll make it look better right now. So I'm going to shorten the y-axis. Instead of from 0 to 10, from 0 to negative 10, let's make it smaller so that we can have a better picture. Let's say we put from negative 3 to 3. Okay, that's a little better. So you can see from 0 to 1, so we are seeing this part of the graph. We're not seeing the left side one. It's like saying that you were having something like this and something like this, and then you're just, let's say, erasing all this, and you're only focusing on this side. So then if you look at it this way, then is the function continuous? Yes. I don't see there's any gap, any jump, any hole from 0 all the way to 1, right? So at least it satisfies that part. Is it continuous over a closed interval? Yes. Is it differentiable on every interval's interior from A through B? It doesn't have to be differentiable at A and B, but it has to be differentiable at every number that is within 0 and 1 in this case. This would be my A and my B. So how do I know if it is differentiable? If it could be differentiable at any number between these two, well, see if you can get the derivative. And the derivative of this function would be 4/5 times x raised to the 4/5 minus 1. So this derivative would be 4/5 x raised to the this would be 5/5, right? And let me, this one looks not very good. So 1 would be 5/5, so this would be negative 1/5. So if you simplify this, well, you have to send the negative exponent to the denominator, and we can make it as a radical. So 4 over 5 times the 5th root of x. That's the derivative. If I would like to substitute any number within this interval from 0 all the way to 1, and it says here that I don't have to include the a and the b, so I don't have to include the 0 and the 1. Every time that you put any number you want between 0 and 1 here into this x, you're going to get a solution. So it is differentiable. That's what it means. If it exists, if you can get a value after substituting any number within this interval into this x. Maybe if you substitute the 0, you're going to say you're going to get an undefined if you put 0 here into the x. But because of the theorem says that as long as it is differentiable between a and b, or throughout a and b, but not at a and b necessarily, because of this type of parenthesis, then we're safe. So then this, it's continuous for every point. Yes, it satisfies the definition of the intermediate value theorem. Yes, f of x is continuous for every point on the closed interval from 0 to 1, and differentiable for every point on the open interval from 0 to 1. It's not going to be differentiable at 0, but it doesn't affect the definition. So it does satisfy the definition. And that's basically it. So what you can do is quick way, graph it, look at it, see if there's any type of discontinuity on that closed interval, and then try to see if you can obtain the derivative. And if it is possible, then just imagine what would happen if you substitute any value within this interval. If it is possible to always obtain an answer, then it's differentiable at every number between this interval. Doesn't matter if it is not differentiable at 0 or 1 at the endpoints of this interval. That would be that one. This one will be the exact same thing. You have the view and example, so I'm going to skip this one to concentrate on this one, which is going to take us longer. So for what values of a, m, and b does the function f of x satisfy the hypothesis of the mean value theorem on the interval from 0 to 4? So if we observe this piecewise function, we see that, for example, when f of x is equals, on the f of x function, we have three functions here, right? So it says that the solution for when x is 0, it's going to be 2. When x is 0, this is the domain, right? The restrictions on the domain of each of these three functions. When x is 0, this is 2. When x is between 0 and 2, but notice that you're not including the 0 and the 2, just any number that it's within, this is the equation we're going to be using. And when x is between 2 and 4, including the 2 and including the 4, this is the function that I'm using. So let's start by saying that, okay, overall, I know I'm telling you that each of these three functions have its own domain. But overall, this piecewise function, what would be the overall domain for the whole thing? Well, the least number that I see for the x here is 0. The greatest number that I see for x here, the greatest value, is 4. So then let's say the following, that f of x is continuous and differentiable on the interval from 0 to 2. This 0 on the first function, it's also here on the second restriction on the domain on the second function. But on the second function, the 0 is not included. On the very first one, yes, it says that if x is equal to 0, the answer is 2. But on the second one, if x is 0, it's not defined on the second one. That's why we're not including the 0. Why we're not including the 2? Because on the second function, it says from if x is between 0 and 2, then you're going to utilize the second function or equation. The thing is that 2 is not a value that is defined on this equation. When x would be 2, you have to skip over to the last equation, right? Because here the 2 is included. So there's a discontinuity there on 0, and there's also a discontinuity at the number 2, because it's defined on some equations, but it's not defined in other ones. So then f of x being the whole piecewise function, is continuous and differentiable on the interval from 0 to 2 and from 2 to 4. Okay, you're going to have to make that distinction and say the domain for the whole thing in 2 parts. Okay, so find the values of a, m, and b that make f of x continuous. So we have to find 3 different values that make this whole function to be, this whole piecewise function to be continuous. That's what, when it says here, for what values of a, m, and b does the function f of x satisfy the hypothesis of the mean value theorem? Okay, so we want to find numbers for a, m, and b that make f of x continuous and differentiable at these 2 values that I put here. So first, we're going to find values that would make f of x continuous and differentiable at x equals 2 and x equals 0. Or I should have said them backwards, right? Starting with the 0. Okay. At x equals 0 and x equals 2. So, we are going to investigate first starting at 0. Okay, so a function, sorry about the telephone ringing. A function f of x is continuous at a point C if, okay. So, here we're going to bring in a concept from before. We know from before that a function f of x is continuous. So what we're trying to find is this that I wrote under number 1. And then this is something that's going to help me find out what numbers are going to make f of x continuous and differentiable at x equals 0 and x equals 2. And that would be this fact. A function is continuous at a point C or x value, like in here, right? If this, and we've talked about this, if f of c is equals to the limit of f of x as x approaches c. So, remember we used to check for continuity, okay? And that's what this is. That if the substitution of a certain number into a function is equal to what the answer of the limit of that function as x approaches that certain value that is substituted into the function. If these 2 answers are equal to each other, then we conclude that the function is continuous at that point C, or at whatever the x value that is given. So that's what we're going to prove right now. For example, if I do what's f of 0, right? So I go to my piecewise function. When x is 0, you want to look at the first domain. When x is 0, the answer is 2, automatically. When x is 0, answer is 2. Okay, so I got that. F of 0 is equals to 2. That's what I was looking for. That's, let's say, this part. Okay, and then it says, find the limit as x approaches 0 of the function f of x. So what you're going to put is when the x's are approaching 0, okay, and you're going to be approaching it, in this case you're going to be looking at this other function. When x is exactly 0, the answer is 2. That's the substitution, that's the evaluation. But when x is approaching 0, then you're going to be using the second equation to do the limit of, to evaluate it. Why? Because in here, this is, imagine this is the x-axis and this is 0, and up to here it's 2. So we are saying that we are approaching the 0 from this side, let's say. So in reality, it's like if you're finding the limit from the right side, but you know that finding the limit of one-sided limits, left side or right side of a certain number, is the same thing as finding the limit as x is approaching 0 from any side. Whatever it's for the one-sided limit, it's going to be for both sides. So then here, what I'm going to do is I'm going to do it by substitution. Negative 0 squared plus 5 times 0 plus 8. So then, out of all this, you're going to get 8. So, a function is continuous at a point C if, and so with this second part you did this. A function f of x is continuous at a point C if this is equals to this. So this, it's 2, and this, it's 8. So all I'm going to do is equal them to each other, and I already found, just by doing that, I found what the value of a must be on this function for f of x to be continuous at the point or at the given value x equals to 0. Because all my analysis right now was with respect to 0. Okay? So we're going to make a little note here. For f of x to be continuous at x equals to 0, a must be equal to 2. And that's already answering one of the things that this question was asking me. Finding a value for a value for b, and a value for m was a. So, okay, that's a. Okay, that would be one of my answers that I was looking for. Okay. Next part. Now we are going to examine. So the second thing is, now let's examine f of x at x equals to 2. So I already examined at x equals to 0. And you're going to do the same thing. So at x equals 2, here on the second equation, it's where x can be 2. On the third equation, I'm sorry, when x is 2, because you have an equal sign here, then mx plus b is the function you're going to be using, or the equation you would be using to evaluate. But then also here on the middle domain, on the second equation, the domain says that it's from 0 to 2, it's just that a 2 is not defined. So that is the discrepancy right there. The 2 being on both intervals, but on one being defined, and another equation not being defined at 2. So what I want to do is find first what's the derivative of the f of x function, but the one where x is not defined at. So negative x squared plus 5x. Now, instead of plus a, as you can see here, instead of plus a, you already know what a is. So you can already substitute that a by this 2. Right? That would be this number. So, let's find the derivative of this. Negative 2x plus 5 would be the derivative. And then, now we're going to find also the derivative of the other function, of this one, where x can be 2. So the derivative of f of x equals mx plus b. So assuming that m has to be a number, right? Like if it is a 2, a 3, or whatever it is, that's what we are probably barely going to find out. So the derivative of mx would just be m. Because if you have 2x, let's say, what's the derivative of 2x? 2. The 3x, 3. The derivative of b, which is a constant, is 0. So then the derivative of mx plus b is just m. So now equal the derivative to each other. Okay. Why? It says that to find, in order to find the value of m that makes f of x differentiable at x equals to 2. So what it means is that if I plug in 2 into the second equation into the x, or if I plug in 2 into the second equation on the x, into the second one or the third one, I want to get the same answer for both. That's what it means. So you're going to get this by setting. By setting the one-sided derivative at this point equal to each other. Okay, why are you going to equal them to each other? Because if you're finding the limit or the derivative, let's say of this function, this one in the middle, as x is approaching 2, so let's say this is 0 and this is 2. Because the interval is between 0 and 2, right? You would be approaching the 2, but from the right side. That would be as x approaches 2 from the left side. Oops. I said from the right side, but it should be from the left side, right? Coming from the negative, not the negative numbers, but from the smaller numbers than 2. From 0, going towards the 2. 0.1, 0.2, 0.3, 1, and so forth. But if you are going to be finding the limit, which is what I did, I found the limit, but with the shortcut of the formulas for the derivative of this function, and I am also interested in approaching the 2. First of all, here it's included. Sorry, here it's supposed to be not from 0 to 2, but from 2 to 4. So then now I'm trying to approach 2, but from the left side. That means that x is approaching 2, but from a positive side. Okay. So that's why you have to equal to each other. It's like finding the limit from both sides, but you did it in a shortcut way with the formulas to find the derivative, and you're going to equal them to each other now. So this negative 2x plus 5 is equals to m. Okay. So then all you have to do is solve for m, right? Because what's going to be my x? The number that I'm analyzing at. So negative 2 times 2 plus 5 equals to m. So negative 4 plus 5 equals to m. So then this would be 1. M is 1. And that's another value we were looking for. What was the value for m? 1. Okay. So we say here, for f of x to be differentiable at x equals 2, m has to be 1. Okay, so I already know the letter A, I know the letter M. So I can start constructing this piecewise function a little different. F of x is equals to 2 when x is 0. Negative x squared plus 5x plus 2 when x is between 0 and 2. And instead of mx plus b, it's going to be 1x plus b, which could only be simply x plus b. You don't have to use the 1, right? But what I'm doing is instead of mx plus b, I'm just simply substituting here 1x plus b, right? Which that's what this part would be. This would be for when x is between 2 and 4. And this part, let me make it over here. Okay. So for the functions to be continuous and differentiable at 0, I already figured out what this value a had to be. For it to be differentiable and continuous at 2, I already have part of what I need, which I needed the b. I already figured it out. That's what I got here. I still need to figure out the b. That's what I don't know yet. And that's what we're going to figure out next. So we're going to put here that I'm going to do something like I did in this previous step, where I equal to each other the derivatives, which was a shortcut way of finding the limit, as x was approaching 2 in this case, from both sides, right? Well, now I want to know, as x is approaching 2, what would be the limit of this function, the exact evaluation of the limit. So for f of x to be continuous at x equals 2, then f of 2 has to be the same thing as the limit as x approaches 2 of the function f of x. So to do this part is telling me that I have to do the limit from both sides in reality, right? So I have to do what is the limit as x approaches 2 from the left side of f of x. And what's f of x? Well, the functions that we are looking for right now, it's going to be this one and this one. So one is approaching 2 from the negative side, which would be this one right here, this first one, right? From the negative side, you're going to be using negative x squared plus 5x plus 2. And let me move this arrow more to this way. And then the limit as x approaches 2 from the positive side, so that would be this one, the second one, which I already know the value for m, which was 1, right? So I can simply write here x plus b. Instead of 1x plus b, just simply x plus b. Okay, so now evaluating this 2, this is going to be the same thing as substituting into the function, and all this being equal to 8. And for this one, it's basically just putting 2 plus b, right? Because you're just going to put the 2 into the x. So what I have to do next is going back to where I started, which I wanted to say that this was equal to all this, right? So what's f of 2? Well, isn't it f of 2 the same thing as what you did when you substituted into f of x, right? So into negative, where here, what happens if I put a 2 here, now that I have a value for a here, which is also 2, by the way. So negative 2 squared plus 5 times 2 plus 2. So all this f of 2, it's going to give me nothing more than 8, right? Which is the same thing as what I had already gotten here. But the thing is that I'm trying to set all this which is 8, equal to all this, which is going to be equal to 2 plus b. Okay. So with this, I'm saying that I'm trying to equal to each other. I'm going to write here. Let me give myself some room. This would be, this 8 would be the answer of the limit of f of x as x approaches 2 from the negative side, but at the same time, that's the answer of the substitution, right? Of 2 into that function, which is this f of 2. So this is the same thing. And then, on the other hand, this part, it's the limit as x approaches 2 from the positive side of x plus b, right? So if I try to find b, which is what I was missing, all I have to do is subtract 2, and this would be 6 equals to b. Looks like a minus in here, but it's an equal sign. And so that's the missing value, b, the third one that I was missing. So how is my function going to be looking like so that it satisfies the definition of the hypothesis of the mean value theorem? So we're going to put here, so for the function f of x to satisfy the hypothesis of the mean value theorem on the interval specifically given to us here. On the interval, and see what I'm going to put here, from 0 to 4. That means that for this piecewise function to not have any any sort of discontinuity, not jumps, no cost, nothing. So then I'm considering it from 0 all the way to 4 as if it was a single piece, all this, okay, all this together. So from 0 to 4, then the function has to look like this following. F of x equals 2 when x is 0, negative x squared plus 5x plus 2 when x is between 0 and 2, and x plus x when x is between 2 and 4. Okay. So what was my m? My m was a 1. What was my b? My b is 6. And what was my a? My a is 2. Okay. And so that would be this problem. Kind of lengthy, but I mean, that's what it is. Okay, the next ones get a little bit easier. This one says, find the value or values of c that satisfy the equation, which is, this is the equation that we were given in the intermediate value theorem, in the conclusion of the mean value theorem for the following function and interval. So all you have to do for this one is follow the formula. So this is going to be a, this is going to be b. So I have to show that this is true. So we're going to do 3 times 2 squared minus 5 times 2 minus 2. Okay. So all this would be f of b minus f of a. So minus 3 times negative 3 squared minus 5 times negative 3 minus 2. All of this divided by b, 2 minus a negative 3. All of this is just this side. Now, equals to f prime of c. So get the derivative, which is going to be 6x minus 5, the derivative of f of x. Oh, and substitute into the x the given value c. So we don't know a specific number that they're being asked about that is within. We know that that c has to be a number that's within this interval. But because I don't know what it is, I'm just going to call that x to be c. Instead of x, use c, just to satisfy this, this equation, right? So then when you work all this out, this is going to be 0 minus 40 over 5 equals 6c minus 5. So this is going to be a negative 40 over 5 equals 6c minus 5. And this would be negative 8 equals 6c minus 5. So you move the 5 to the other side. So that's going to be a negative 3 equals 6c, divide by 6. So c is going to be negative 3 over 6, which can be reduced or simplified to negative 1/2. So, question is, find the value or values of c that satisfy this equation. That's what it is. That's why you wanted to leave this x on the right side in terms of c. Besides, that's what it was saying here, right? Get the derivative in terms of x's, but then the x's turn them into c, so that you can solve for that variable. And that's what the answer is. That's the value that the question is asking about. Okay. Okay, so that would be that one. I'm going to skip this one because it's the same idea as the previous one. This one too. Okay, I'm going to skip to this. Corollary 1 says, if f prime of x is equals to 0, so if the derivative of a function is equals to 0 at a point x of an open interval a through b, then f of x is equals to z. For all x, for all the x's within a through b, within the open interval a through b, where c is a constant. Okay. If f prime, so it's saying here, there's the derivative of a function that you're going to set equal to 0. And it's going to be equal to 0 at each point x, it says, of an open interval from a through b. Then f of x is equals to c, then not the derivative, the original. F of x is equals to this constant. C represents a constant, and that's what it's saying there. Okay, for all the x's that are within this open interval. Corollary 2 says, if f prime is equals to g prime. So if you get the derivative of one function and then you get the derivative of the other one and you equal them to each other, or they're equal to each other, at each point x in an open interval or within an open interval a through b, then there exists a constant c such that if you get one function, not the derivative, just the original of f of x, then g of x, the original g of x, plus some number, plus some constant, it's equal to f of x, equals to the other function. So the addition of one of these equations or one of these functions plus some number, some constant, it has to be the same thing as the other equation or the other function. And this is true for all x's that are within the open interval from a through b. That is that also, contrary to that, if you subtract, just isolate for the c, if you subtract f of x minus g of x, the answer is the constant that is within that interval, right? That's what this last part is saying right here. So, let's see that illustrated in this problem. It says, suppose that f prime of x is equal to 2x. So this is the derivative of some original function, right? F of x, for all x. We don't know, or it's not given to us right now what was f of x. I just know the derivative of a function, it's already here. And then letter A says, find f of negative 1 if f of 0 is 0. Okay, so they're asking me to find f of negative 1 given that f of 0 is 0. So I need to know what was the original function prior to f prime of x, right? So this is f prime of x, and I want to go one step before we took the derivative and we ended up with this. So the original f of x, if I am trying to use my logic, has to be probably x squared. Like imagine you put this number up here and that becomes x squared. And if you do the derivative of this, you bring the 2 to the front and you subtract 1 to the exponent, and that's how you ended up with 2x. So that makes sense. So now what I have to do is say, okay, based on this corollary number 2, I'm going to say f of x is equals to g of x plus c for some constant c. So f of x is equals to, what would be g of x? I called it f of x here, but just to use the same variables as they're using on the corollary, I should have used g of x. So g of x is going to be the x squared plus the c. Now, given I have f of 0 being 0, so f of 0 is equals to 0 squared, okay, so this x value is the one that you are substituting here, and also here in every single x, plus the c, I don't know what that is. In this part, f of 0, it says here that f of 0 is 0. So that's what you're going to replace with this part. This is 0 from where? From this. Let me make another color. From here. Okay. Equals to 0 squared plus c, which what's going to be 0 squared? Just simply 0. Plus c equals to 0. So if you have to solve for c, c is equals to 0. That is the constant that was missing here on this formula or this equation. So then a, so all I was doing here is trying to use this part to find the value for c, the specific constant number that would satisfy that equation. So now that I know it, this, all I have to do is say, okay, so f of x is equals to x squared plus the c. And in reality, what I'm trying to find is f of negative 1. So this number, you're going to put it here, and you're going to put it here as well. So f of negative 1 equals negative 1 squared plus c. Oh, and instead of the c, let's already replace the 0, which I found to be c. Is it always going to be 0? No, it's just a coincidence. So this would be a 1 plus 0, it's just going to be 1. So f of negative 1 is 1, and that's what you were looking for. F of negative 1 is equals to what number? Okay, and we were able to get there thanks to corollary number 2. For b, it's going to be the same thing. Okay. For b, let me right here below. So I have been given to find f of negative 1, given that f of 3 is 4. So now that you did the formula, should be like, now that you did this one, should be a little bit easier. So I'm still using the same derivative for all three. So g of x is going to be the same for all three, for a, b, and c. So then you're going to put here f of x is equals to x squared plus c. So f, you're going to put here something that you know the value of. So you're not going to put the negative 1 yet because you're not ready for that. F of 3 equals 3 squared plus the c. But this f of 3 is 4. And so 4 is equals to 9 plus c. So when you move the 9 to the other side by subtracting, c is equals to negative 5. So what you're trying to find is what f of negative 1, right? So f of x equals x squared plus the c. So f of negative 1 is equals to negative 1 squared, and I was going to put a plus, but since the c is a negative number, let's put it as a minus 5 already. So f of negative 1 is going to be 1 minus 5, which is negative 4. Right? And that's what the answer is for this part. Okay. One more. Let's do letter C. So given for letter C, we have find f of negative 1, given that f of negative 4 is 20. So I need to find this, right? Also here I didn't say that that's what I wanted to find. Find. Here I was also trying to find this. It was there, right? Just wanted to write it again. So f of x equals x squared plus c. So f of negative 4 equals negative 4 squared plus the c. This would be 20. So this would be 16 plus c. You move the 16 to the other side, so 20 minus 16 is going to be a 4. So this 4, you're going to use it to come up with the actual value, x value you were looking for. So negative 1 squared plus 4. So f of negative 1 is going to be 1 plus 4, it's going to be 5. So f of negative 1 is 5, and that's what this is, 5. Okay. For the next one, it says find all possible functions with the given derivative. So something similar to what we did here at the beginning, okay? And using those formulas from the corollary. So if I have f prime to be, so I'm going to write it here. I have f prime of x to the 6th power. But I want to go one step beyond. Find all possible functions with the given derivative. So then I have to think of another function where when I did the derivative, when I would do the derivative of that function, it's going to look like this. So remember when you do the derivative, like if you have, let's say, a variable raised to an exponent, you bring the exponent to the front and you subtract 1 to the exponent, right? So you bring the exponent to the front to do what? To multiply times something. So let's say this is my x and there's an exponent. So when I'm doing the derivative, right? Just thinking of the power rule. We bring the exponent to the front, so that exponent comes to the front and it's going to multiply times this that was already there. And then what do? You subtract 1 from the exponent, right? From that old exponent. Whatever was here, you always do minus 1 to it. So now you have to kind of think backwards. So instead of subtracting 1 to the exponent, perhaps you want to think of adding 1 to the exponent, because you're going backwards. That's what you're doing. So 6 plus 1. So that was the original exponent. 6 plus 1 was 7. That was the original. So that 7, when brought to the front, you may think, and what happened to the 7, right? If I put the 7 up here, why is it not showing over here? Because probably your original function was dividing by 7 as well. That way, when you simplify this, these two 7s cancel. In reality, see here. Yes, so here what I was trying to write, it was just to show you like what probably was the process you went before to get this. So if the exponent, if you add 1 to the exponent, that means the exponent was x to the 7th power. And so why is there's no 7 here at the front that was brought to the front of the x? Because I'm not going to move the 7 to the front, I'm just going to leave it there. But probably the original expression had a 7 here. So when you do x to the 7th over 7, so you do the opposite operations of what you do when you get the derivative. When you get the derivative, You bring the number to the front multiplying, but in this case, that number that I was supposedly bringing to the front in multiplication form, I'm putting it as in division form. And instead of subtracting 1 to the exponent 6 here, I'm adding 1, and that's the 7. And actually, that's the 7 that's on the denominator. So instead of subtracting 1 to the exponent, you add 1 to this exponent on the derivative. Instead of multiplying times the old exponent, the original exponent at the front of the x, you use that number, that old exponent, to divide that x to the 7th by that number. And so this technically was the derivative, but if you see how the question asks, it says final possible functions with the given derivative. So all possible functions. So that means that there could be more than one possibility. What could be that more than one possibility? Something like what you were doing in the previous question, where the c, the constant of variation, could be something different every time. So then, depending on the x value, g of x is equals to x to the 7th over 7th plus your constant of variation, which we don't need to find it right now. Okay, they're not asking us to be very specific, just final possible functions. This could give me my possibilities. So all you have to think is on the kind of operations you do when you're getting the derivative of a function, and thinking of doing those operations but in reverse mode, backwards, to obtain the original function. Okay, and that would be that. Let's see if we can practice once more that same concept with this one. So here is, it says final possible functions with the given derivative. So here is my derivative. So I want to go one step beyond. Okay. So remember that you just want to basically do one step, go figure out the equation that was before this, so that when you did the derivative of that, this is what you ended up with. So the easiest one that I can think of probably is going to be this one. This one was probably negative 6x, because if you do the derivative of this, it's just going to be negative 6. Now, this other one here, if this part, I take it to the side to examine it, this would be the same thing as this, and it's going to help me see things easier. So, do the opposite of what you see here. Add 1 to the exponent. Okay, so let me add 1 to the exponent. Okay. Oh, this was a negative, sorry. Negative 2 plus 1. Okay, now I need to think, how did this 5 is up here? Okay. If the original exponent was negative 2 plus 1, that means the original exponent was just a negative 1. So when you bring that negative 1 to the front to multiply times this number, that would make this to be a negative 5. X to the negative 1. Okay, let's try to see if it is true. If I would get, let's assume this is part of y, right? And if I do the derivative of this, would that be equal to this? That's what the question is, if I did this right, if I thought about it correctly. So I bring the negative 1 to the front. I multiply times the negative 5. I do negative 1 minus 1, because I'm always supposed to get to subtract 1 from to get the derivative on the exponent. So 5x to the negative 2, which this is the same thing as 5 over x to the second. So bingo, that's what it is. Here, the function, or not the function, but the expression for this to be the derivative of had to be this part. That's what should have gone there. Minus 5x to the negative 1. So all I did first, if you see step by step, is I brought this x squared to the top as a negative. Then I thought, for this to be the derivative, I need to add 1 to the exponent. That gave me a negative 1. And then I thought, what about the 5 that's already there at the front? When this negative 1 came to the front, if it would have just come out over here to the front by itself, that would have been a negative 5, right? Yes. And so then I said, okay, so this is probably my original. But here at this point, I was just, let's test it. How? By getting the first derivative of this. And it worked out because I got what the actual derivative is that they're showing me. The only thing that I want to make sure I don't forget to put is the plus c. So this is going to look better if I write it like this. Negative 6x minus 5 over x plus c. And that's what this would be. Okay, so this one, find the function with the given derivative whose graph passes through the point. Find the function, find the original function with this given derivative whose graph passes through that point. Okay, so I need to go backwards, finding what the original of this was, one step before. So if this is 2x, probably this term 2x was x squared at some point. If you do the derivative of this, that's 2x. Makes sense. What could have been the original term for the derivative of it to be minus 5? It was probably minus 5x, right? Plus c, because there may be many variations. Every time you're finding what was the original function of a derivative, you're going to put plus c all the time. So then, now I want to find the function with the given derivative whose graph passes through that point. So all you're going to do is substitute what's given from that point into the corresponding variable. So all this is 4, 1 minus 5 plus c. So 4 is equals to negative 4 plus c. So c is going to be 8. Okay, so then with this, the function I was looking for is x squared minus 5x plus 8. This was the original. If you take the derivative of this, that should be this right here. And it matches perfectly. Okay. So what you are doing here is a little bit of an introduction to antiderivative. That's what you're doing. Okay. There will be formulas that we will learn in a little bit more. But first we're learning them, let's say, the hard way, like analyzing what we are doing. Okay, so this next one says, it's the same thing as the one that I just did, so I'm going to skip it. This one, just because it's more of an application, but doing the same thing. Given the velocity, v is velocity is equal to the derivative of s with respect to t, and the initial position of a body moving along a coordinate line, find the body's position at time t. So remember when we used to say that the velocity was the first derivative of the position function? Okay, and the position function usually we represent it with the letter s. So I need to go backwards thinking what could have been the original function to this derivative. So okay, if this 9.8 is here, it's because that 9.8 is probably the result of, okay, it's not, there's a 9.8 here, but also look at the exponent on the t, it's a 1. So at some point that t was raised to the second power, right? Because if you add 1 plus 1, the original exponent had to be this. So how is it that 9.8 is here? So then when you brought this to, if you were going to take the derivative, you were going to bring this number to the front, multiply times something, and the result was 9.8. So then 2 times something was 9.8. So in other words, divide 9.8 by 2, which that would be 4.9. 9.8 divided by 2, 4.9. So then 4.9 is the number that had to be here. So I just thought about doing the opposite. If bringing the 2 to the front times something gave me 9.8, then 9.8 divided by that number, it's going to give me the number that was here. The 2 is the derivative of probably 2t, plus 2t, plus the c, plus the c. So It says f s of t, I just forgot to write it like that, 4.9t squared plus 2t plus c. So s of 0 equals 4.9 times 0 squared plus 2 times 0 plus c. So this is going to be 9, this is going to be 0, this is going to be 0, so this is just going to be the c. So the position function is s of t equals 4.9 t squared plus 2t plus 9. Okay, and that's what the answer should be. And okay, so let's see the next one. It's same situation, just a different function. So let me see if I do that one. Yes, let's do this one. Once a certain planet's moon, on a certain planet's moon, the acceleration due to gravity is 2.8 meters per second squared. If a rock is dropped into a crevasse, how fast will it be going just before it hits bottom 32 seconds later? On a certain planet's moon, the acceleration, so the acceleration is the second derivative of the position formula. So first it's s, the position formula, then it's v, the velocity, that's the first derivative. Second derivative is going to be the acceleration. So what they're giving us here is information about the third derivative. Okay. And then it says, if a rock is dropping to a crevasse, how fast will it be going just before it hits bottom 32 seconds later? So how fast, they're asking for the, not for the time, they're giving me the time. 32 seconds later. So how fast, they're asking me for velocity. So they're asking me to figure out what was, it was the position function, then, so this is the original function. Then it's the velocity, which is first derivative. And then it's the acceleration, which is the second derivative. So we know this being this is a of t equals 2.8 meters per second squared. So then v of t, over here I'm going to write v of t is some function whose derivative is this. So again, we're trying to think backwards. So v of t probably look like, if this is 2.8 only, the derivative of v of t had to be 2.8 t. Okay, this one had to be this. The question is, if a rock is dropped into a crevasse, how fast will it be going just before it hits 32 seconds? So then what I have to do is say, find, okay, and this, it's c, right? Because remember that every time you're finding the original function from a derivative, you want to put c. So v of 0, because the rock initially is going to be at rest. So if we assume that, okay, we want to use something that we know. And if this is a rock that is falling, at some point the rock was at rest before it was dropped. So assuming when the rock was at rest, v of 0 okay, then we say v of 0 equals 2.8 times 0 plus the c, plus the constant of variation. So this, when the time was 0, the velocity is 0, right? That's what I missed here. Because this is like saying v of t. When the time is 0, the velocity was 0, what's meters per second, or what's this? Yes, meters per second. Okay. Time is 0, the velocity is 0 meters per second. So then that's why here we put 0 because of this. So then this is 0, so c is equals to 0. So then what I want to find is when the time was 32 seconds, or at 32 seconds later, what was the velocity. So then v of t again equals 2.8t plus c. So v of 32 seconds later plus the constant being 0, then this would be 89.6 meters per second. And that's what we were looking for. Okay, so this concludes this lesson. At the end, the only thing that we have is this review of laws of exponents, okay, which that can help us with figuring out the original functions of derivatives. Okay, so you want to review this. When you're multiplying the same base times the same base, you add the exponents. When you are dividing the same base over the same base, you subtract the exponent, the top minus the bottom. When you have a negative exponent, you can create the reciprocal, where you flip this around, and that way the exponent changes to positive. We already learned that before. And when you have more than one exponent for the same base, you can multiply them this way, okay, or interchange them if you need to. It's the same thing. So that would be it for this lesson.